Okay, homework 1 was supposed to be due Wednesday, right? Okay, if you come to the live class, bring it unless you don't have it. And if you don't, then just wait till the next class. It's not a big deal. In other words, bring it to the next live class. Okay? Okay, so the question was about homework 1, which is officially due on Wednesday the 25th. Are there any questions about anything at this moment? The last thing we were talking about was the waiting time paradox and the exponential distribution and the Poisson process. So what we showed was that under certain reasonable assumptions that if you have a process in which events occur at random, and we defined what we meant by random, meaning essentially that every point is equally likely to have an event, and the instants in time are independent of each other. So if we have such a setup, then if we let x be the times between events, so that would be x1, x2, and so forth, then we proved that under reasonable assumptions, the most reasonable assumptions you could think of, the probability that x exceeds t is e to the minus lambda t, where lambda is the rate at which these arrows occur, or equivalently, its reciprocal is the average time between arrows. And any random variable that has this distribution is said to be exponentially distributed. So in other words, the distribution function for this random variable is 0 when t is negative, and 1 minus e to the minus lambda t when t is not negative. And any random variable that is described by this, we say that x is exponentially distributed as an exponential, exp, with parameter lambda. And then we showed that the exponentially distributed random variable has this memoryless property, which is very important. And memoryless property says that, for example, if I am waiting for an arrow, an event to occur, and at time y it has not yet occurred, then I could ask this question. What's the probability that the time I have to wait for the next event is greater than y plus t, given that it's at least y? So here's y plus t, so this interval is t. So what we're asking is, what's the probability that if I have a Poisson process, this is called a Poisson process, by the way, and that's important name, Poisson process. All right, if I have a Poisson process, then the probability that I have to wait at least t more for an event to occur, given that I've already waited y for the event to occur, that probability is independent of y, of the age, and is just as if we were starting from the beginning. And that's called the memoryless property. And so this turns out to be very important because obviously, in some sense, it simplifies things because it means that you can ignore information that otherwise you might have to consider. But this leads to what's called the waiting time paradox. And the waiting time paradox says, as the example I gave was that suppose that you have a process, let's say for the sake of example that you are that these are taxis. So taxis are arriving at some point in space, a taxi stand, on the average of 1 hour apart, but they're arriving at random according to a Poisson process. So you arrive at some time ordinarily between two adjacent taxis. And so there's going to be a length of time that you're going to have to wait for your next taxi, and there's a length of time by which you missed the last taxi. A is called the age of the interval. That's the time looking back to the last taxi. R is called the remaining time. That's the time looking forward to the next taxi. And the question was, what's the expected value of r, given that, in this case, the expected value of x, the time between taxis, is 1 hour. And so the common sense answer is that, well, if the average time between taxis is an hour, then the average time I would have to wait is half an hour. But that's incorrect, because the Markov property, which I just proved, says that the length of time you would have to wait until the next event is independent of the past, and it's just as if you were starting from the beginning. So therefore, the average time you would have to wait for a taxi would be 1 hour. I'll write it like this. That's the common sense answer, but that's wrong. So the answer is 1 hour, because the process is just as if it were starting from the beginning. And by that argument, by symmetry, then you would say, well, the average time looking back to the last taxi must also be 1 hour. And therefore, the average time between taxis, I'll call that I. That's the interval during which you arrived. And the average length of that interval must be the average length of the age plus the average length of the remainder, and that, of course, turns out to be 2. But 2 does not equal 1, so that seems to be a contradiction. And so the question was, why is that? And the answer is, well, we'll examine that a little bit more deeply in homework number 2. But that's where we quit. Now, I wanted to say something about the Poisson process. So before I go on to this stuff again, let me go back and look at the Poisson process from another point of view. What we did here was we made a mathematical model, a model of reality, and that model produced the exponential distribution. And so we said that that means that if the times between arrows are independent, identically distributed random variables with this distribution, with this exponential distribution, then we say that we have a Poisson process. Now, I want to ask the question a different way. Instead of telling you how much time elapses between arrows, I want to fix a length of time and ask for the distribution of the number of arrows that occur in that time. So let's say that here is 0, and here's t. Let's see if I get one of these things that has more ink in it. Okay, there's 0, there's t, and these arrows are occurring according to a Poisson process. In other words, the times between arrows are independent, identically distributed with the exponential distribution. And the question I want to ask is, what's the probability that in this interval of length t, I will have exactly, I think we're running out of ink here. There we go. I want to calculate the probability that in the interval of length t, I have exactly j arrivals. So in other words, this is another characterization of the Poisson process, because originally I expressed it in terms of the times between arrivals, which is a continuous distribution. And here I want to fix the time and ask for the number of arrivals that occurs in that time, which is discrete distribution. But obviously, they should be equivalent, because if I could tell you how much time elapses between things, I should be able to tell you how many occur in a fixed time. And conversely, if I could tell you for any fixed time how many occur, then I ought to be able to tell you how much time is between them. So these are going to be two equivalent representations of the same thing. But this argument is worth something. Okay, so here is the way I want to make the argument. I'm going to say that the probability, and by the way, what I'm talking about here is exercise 17 on page 51 and 52. So let me write that down. Exercise 17, starting on page 51 in the textbook. And remember that the solutions of all of the problems in the textbook are worked out in detail in the solutions manual, which you can download from the website. So actually, the statement of that problem is a little bit more general. What it says is, suppose that the times between these arrivals has a distribution G, capital G. So that means I can write this probability this way. What I'll say is that, first of all, G of, let's call it x, G of x is the distribution function of the time between arrows. In our particular case, it's going to be exponential. That means that the differential of that would be the density function times dx if this were differentiable. Now, later on in the course, we'll see that we can treat discrete and continuous random variables using the same formalism. So what I'm writing down here is what's going to be called a Riemann-Stieltjes integral. But for our purposes, we should just interpret this thing right here as the density function of this random variable times dx. So this represents the probability. Let me draw a picture here. This represents the probability that, roughly speaking, that at time x, I have my next arrow. So imagine that times between arrows have this distribution function, which means that this formalism stands for density function dx. So this then would represent the probability, if this is 0, that my first arrow occurs at time x. And if I'm to have j arrows between 0 and t, that means that I must have j minus 1 arrows between x and t. So the probability of that is p sub j minus 1 t minus x, and then I add those up over all possible values of x, which is from 0 to t. Okay, so what this does is this represents the probability of having j arrows in a fixed time in terms of the probability of having j minus 1 arrows. So what that means is that if I know the starting point, in other words, if I know p0, then I should, and if I know the g, then I should be able to get p1 from that, and then p2 from that, and so forth. So in other words, these probabilities are defined iteratively, and if everything works out right, I should be able to get a formula for everything. Okay, so the argument is that the probability that I have j arrows between 0 and t is the probability that my first arrow occurs at time x times the probability that between x and t I have exactly j minus 1 other arrows. And this presumes that the times between arrows are independent, identically distributed with this distribution function, and that an arrow occurred at time 0. That's where I'm starting my measurement. Question?
So the probability, the p sub 0 of t is the probability that there are no errors
In time t. Right.
and that would be 1 minus the g of t.
That's right. So the first thing I have to do is, if I decide that my distribution function of times between arrows is g, then the probability of no arrows is the probability the time to the first arrow is greater than t. And if capital G is the probability of less than t, that means that p0 is 1 minus g of t. So you tell me the g, that gives me p0, and I plug the g into there, and that gives me p1. And then I plug the p1 into there, and that gives me p2, and so forth. Now, in particular, if a Poisson process then that means that g of t is exponential. So g of t would be equal to 1 minus e to the minus lambda t. Or in other words, p0 would be equal to 1 minus that, or p0 would be equal to e to the minus lambda t. Okay, so now I just turn the crank. So let me go back over here. then I would get Pj is equal to, well, let's see, let me start from the beginning here. I would get P1 of t is equal to the integral from 0 to t of P0 of t minus x e to the minus lambda t minus x times the density function, which would be, for an exponential, would be lambda e to the minus lambda x dx. Okay, this thing right here, that's the density function, which we're calling little g of x dx. Okay, well, that's easy enough to evaluate. In fact, you can see that the e to the minus lambda x cancels with the e to the plus lambda x. I'm left with lambda e to the minus lambda t, which I take outside the integral sign because I'm integrating with respect to x. And that integral then is t. And so this is a simple problem. The answer is lambda t e to the minus lambda t. Okay, so there's P1. I take P1, I put it back in here, this equation right here. I get P2, and so forth. And once you see that now, it's easy to verify that here is the final result. I'll write it here, right here. Poisson process. Let me erase this waiting time paradox argument, although we'll get back to that. If I plug, it's easy to show, let me put it this way, that Pj of t is equal to lambda t to the j over j factorial e to the minus lambda t, for j equals 0, 1, 2, and so on. In other words, this is the solution to this. You can see that when j is equal to 1, that's exactly the answer I got here. So now you could prove by induction. I could simply take this general expression, put it in here, and replace this by lambda e to the minus lambda x, because we're talking about the Poisson process, exponential interarrival times, and then see that what results is exactly this form right here. So the bottom line is, if the times between arrivals are independent, identical exponential variables, that is the Poisson process, then the distribution of the number of arrivals in a fixed time has this formula, which is called the Poisson distribution. So there's the Poisson process, which describes the stochastic process that we derived, and then the Poisson distribution is a discrete distribution that describes the number of arrivals in a fixed time for that process. So if we have exponential interarrival times, then we have a Poisson distribution for the number of arrivals in a fixed time. Conversely, if this describes the number of arrivals in a fixed time, then the times between the arrivals must be exponentially distributed. That's easy to see because all I have to do is set j to 0. And when I set j to 0, that gives me, this part becomes 1, and that gives me e to the minus lambda t, which, as we said at the beginning, is the same thing as 1 minus the distribution function of the times between arrivals. So if we have exponential interarrival times, then we have a Poisson distribution for the number of arrivals in a fixed time. And if we have a Poisson distribution for the number of arrivals in a fixed time, then we have exponential interarrival times. Therefore, they imply each other, and the name of that process is said to be a Poisson process. And so when I talk about arrivals occurring according to a Poisson process, in my mathematical analysis, that means that I can describe them either in terms of the interarrival times, which is exponential, or in terms of the number of arrivals in a fixed time, which is the Poisson distribution. So I go back and forth between which description I want to use, depending on what my mathematical structure is, to make things as simple as possible. So that's the Poisson process. Okay, any questions about that? Now, this is a general statement, and so if you go to exercise 17 on page 51, what it does is it points this out and then asks you to assume that the g here is exponential, turn the crank, and show that that produces this. So and this is standard stuff. Everybody knows this. Standard stuff in stochastic processes. Okay, now in homework 1, I told you how to do everything except how to generate the distributions of the arrival times, the inter-arrival times, and the service times. And so now I want to show you how to do that, and then we'll get back to this waiting time paradox. Okay, so let's take a look back at homework 1. Let's see. I have a copy here. Okay, in homework 1, there were 2 instructions. 130 and 200. Okay, so there's instruction 130, which said that the inter-arrival times are something, and then there was instruction 200, which said that the service times were something, and you had to fill in that something. But then I told you what it was so you could actually run the problem, although there was no way for you at that time to understand what this was about. And the viewpoint is that you had 2 urns here. So the first urn is called IA, inter-arrival times. The second one is X, which stands for the service times. And you imagine that there are tickets in each urn. And when you run the simulation, the picture you have in your mind, or picture I have in my mind anyhow, is you reach into the first urn and you pull out a number and you call that the inter-arrival time. Then when you get to here, you reach into the second term, you pull out a ticket or a number, and you call that the service time, and you do that over and over again. And so the stochastic properties, the randomness of the inter-arrival times is represented by the numbers in this urn. And the randomness of the service times is represented by the numbers in this urn. And what you want to do is you want to have the computer generate those numbers. And what I said is that if, for example, I have exponential inter-arrival times, that is a Poisson process, then this instruction would be of this form. It would be minus 1 over the arrival rate, which in this case was 4, 1 over the lambda, times the log, that's supposedly a natural log, but this is in basic, so they use log, of 1 minus RND. And RND represents a number given directly by the random number generator, which is supposed to be uniformly distributed numbers between 0 and 1. So the question is, okay, why does that generate exponential inter-arrival times? Why does this generate a Poisson process? Similarly, if I had exponential service times, as in the first case of this homework problem, then the service times had an average of, what was it, 2.4? Okay, so then the instruction to generate exponentially distributed service times, whose average is 2.4, would be minus 2.4 times the log of 1 minus a random number. So I gave you those instructions and told you to use them, and now I want to explain why it is that those are the instructions we use. Okay, any questions? Make sense? Yeah. That's okay. The question is, why do you have 1 minus the random number? In fact, I could use the random number directly because, as we'll show in a short time, if a random variable is uniform between 0 and 1, then 1 minus that random variable, which defines a new random variable, is also uniform between 0 and 1. So if I wanted to make the simulation more efficient, I'd just replace 1 minus RND by RND. And in the future, we can do that. The reason it's 1 minus is when I make the original derivation, it will turn out that the 1 minus is in there. So it's one more step to say, okay, so I'm going to be more efficient and show that I didn't have to use 1 minus. I could have used the original. Okay, but like in an undergraduate course, I don't like to do that because then that's one more step, which is in some sense, obscures what's going on, because then more understanding is necessary to actually get to directly to the formula. Okay, so now what I'm going to describe is what's called the inverse transform method. So I'll put that over here. So those of you who took the stochastic models course, STA 4821, you should know this because, in fact, this was one of the main topics that's covered in that course, although I think a lot of people just learn the formulas and don't really understand why it works. So this is the inverse transform method. Inverse. In my opinion, this is very important, and in most probability courses, I think, that are taught from a mathematical point of view, this is not covered. And in my opinion, this is the one important topic that makes probability accessible through simulation, so you can actually see experimentally what probability is all about. So I think this is a very important topic. So the inverse transform method, and what it's for is to use the random number generator. To use the random number generator, which the computer has built in, to generate random variable values according to any specified distribution function. All right, so the computer has built into it a random number generator which generates numbers that are uniform between 0 and 1. At least it's supposed to. That's its purpose. And in fact, it's actually a pseudo-random number generator because it generates a stream of numbers that are determined by a deterministic algorithm. So they're not truly random, they're pseudo-random or false random, but they appear to be random in the sense that if you saw the string of numbers and you didn't know how it was constructed and you applied statistical tests of randomness to it, then it would appear that the numbers were obtained by that old experiment. The idea that you have this dial and you flick it and you pick out a number on the circumference of that circle between 0 and 1. So there's two parts to this inverse transform method. The first part is an algorithm. That is, I want to tell you what to do. And then the second part is to prove that if you do that, it works. So the first part is just a recipe. And so the idea is this. First, I'll draw a picture here. Suppose that I have a distribution function that corresponds to the description of the tickets in the urn that I want to generate. And I'll call that capital G. And I have to draw a picture here, so if I'm going to draw a picture, I have to draw a picture of something. So I'll draw it as if it were an exponential distribution function, but it could be any distribution function. So the requirement for a distribution function is that it gives a value between 0 and 1. It starts out at 0, it ends up at 1, and it never decreases. So any such function is a distribution function. But I'm going to call, this is what an exponential distribution function would look like. And so I'm going to call the formula right there capital G of U. That's U. Okay, now what I'm going to do is I'm going to pick a random number. I'm going to spin this dial. I'm going to ask the computer to give me a random number, and I'm going to put that random number on the vertical axis project over to the curve and down. So this is my random number, and I'm going to call this projection the random variable value. So what it does is it takes these numbers, which are random, and makes new random numbers by distorting them according to the curve that I project to. And then I claim that if the r's are in fact uniform between 0 and 1, then the x's will have as their distribution function whatever the formula is that that curve represents. Okay, so let me write that down. I'll say to generate a value x, put random number call it r on the vertical axis project over to curve G and down to horizontal axis. Okay, that's the algorithm. Now I want to prove that it works. Okay, so the way I'm going to do that is I'll imagine that here's a point T. And if that's T, then this value over here would be G of T. And I want to show that if R is uniform, then the x's have as their distribution function G of T. Okay, so I need to go over here. I'll do that right here. Let's see if I can find a better one of these guys. This one doesn't look like it's going to work either. Okay, so this is our algorithm. Okay, so here's our algorithm. Nope. Could we get new magic markers? These things are running out. I don't know what this is. Let's see if this works. This looks more like a pen. Algorithm. Yeah, maybe this is good enough. Okay, so that's the algorithm. Okay, now here's my theorem. So 2. Theorem. The theorem says, see, I think I got to wait till the cameraman comes back. He's looking to get some ink. So, anybody know any jokes? Because I don't think the camera's going to follow me. Here we go. Thank you. Okay. All right. Wow. This is really high quality here. Okay, let's see what happens. All right, let's see if the camera gets back here. Okay, so here's where we are. There's our algorithm. Here's the theorem. So the theorem says, if the R that I drew on the board over there is uniform 0, 1, then x, the value that I get by, I should say it this way, then the distribution function of the random variable x that I get by making this projection, then f sub x of t will be g of t. In other words, when I project when I make my projection, there's my R. If the R's are uniform 0, 1, then the x's that result will have as their distribution function whatever happens to be the formula for that curve. Okay, so why is that? This is really simple. Here's my proof. Okay, the first thing what I'm trying to do is I'm trying to calculate the distribution function of x evaluated at t. By definition, that's the probability that x is less than or equal to t. Okay, if you go over here and look at this diagram, you can see, here we go. If you go over here and look at this diagram, you can see that if x is less than or equal to t, then r must be less than or equal to g of t. So the probability that x is less than or equal to t is the probability that r is less than or equal to g of t. Okay, that's simple enough. What is that? By definition, that's the distribution function of r evaluated at g of t. What's that? Well, of course, that depends on what the distribution function of r is. We're assuming here that r is uniform 0, 1. So now I'm going to use that assumption right here. Okay. Now, if r is uniform 0, 1, what does that mean? That means that the distribution function of r, let's call it x here, at x is equal to x as long as x lies between 0 and 1. That's the definition of the uniform distribution. So therefore, the distribution function evaluated at g of t, since g of t, being a distribution function itself, necessarily lies between 0 and 1, must be g of t. Well, case closed. The distribution function of x is g, which is the formula that was used for this curve to which you are projecting. Okay? That's one of these proofs where sort of the hand is quicker than the eye. I mean, it goes right by. It's so simple, and yet it's very important and sort of mysterious. But there it is. It proves it. So are there any questions about that? Okay, this is straightforward, right? I know from past experience that a lot of students have a lot of trouble with this, but that's usually undergraduates. So everybody's okay with this. Anybody who isn't okay is not saying. I guess everybody is okay with it. Okay, so that means that let's implement that for this particular case, for the case of an exponential. Okay, so going back over to here. Okay, so now my g has formula 1 minus e to the minus lambda u here. Or, okay, so what I'm going to say then is this. I'm going to say that when I plug in x into this formula and I get r, then that means that r is equal to 1 minus e to the minus lambda x. So therefore, solving this equation, I can write e to the minus lambda x is equal to 1 minus r, or taking logarithms of both sides, I get minus lambda x is equal to the natural log of 1 minus r, or in other words, x is equal to 1 over lambda times the natural log of 1 minus r. I forgot the minus sign. Or equivalently, in basic, that means that x is equal to minus 1 over lambda, whatever that is, that's going to be some number, times the natural log of 1 minus RND. So now, if we go back to our homework 1, if we want to have Poisson arrivals, which means exponential inter-arrival times, with a rate of 4, that means that the average time between arrivals would be 1/4. That would be the 1 over lambda. Lambda would be 4 in this example. So this instruction then would generate exponential inter-arrival times. In other words, a Poisson process with a rate of 4 arrivals per unit time. Similarly, this would generate exponential service times with an average value of 2.4. Okay, so that's where that comes from. Now, the observation was made that I don't really have to use 1 minus RND. I could use RND directly. Okay, so let me show that. Okay, so the reason I wrote 1 minus RND is because when I go through the proof, that's exactly the way it comes out. Okay, but now I want to make a little bit more sophisticated argument. Here's a general statement. Suppose I say we have a random variable y, which is equal to 1 minus x. And I want to find the distribution function of y. So that's the probability that y is less than or equal to t. That's equal to the probability or the distribution function. Let me say it that way. That's equal to the probability, I'll write it like that, that 1 minus x is less than or equal to t. But that's equal to the probability that x is, putting the x on this side and bringing a t over to that side, x is greater than or equal to 1 minus t. But since that's a greater than, that's the same thing as 1 minus the distribution function of x evaluated at 1 minus t. Now, if x is uniform 0, 1, then the distribution function at any argument is the same as that argument. So therefore, this would be equal to 1 minus t, which is the same as t, which means that the distribution function of y is equal to t, assuming that t lies between 0 and 1, of course. So therefore, that means that y is uniform 0, 1. So that means that in these equations, every place where I have a log of 1 minus RND, I could just as well replace it by RND. I get different numbers, but statistically they're the same. They have the same distribution. And this makes things run faster because you don't have to do this subtraction every time. So it's a minor point, but it's more elegant than not. Okay, so now we can go back to the waiting time paradox. So any questions here? Everything okay? Okay, so I want to look at homework number 2, which addresses the waiting time paradox. And I don't remember whether I asked you to download it and bring it with you, so let me pass these out. Okay, just... Oh, by the way, I guess I should say one last thing about this, just to make everything as simple as possible. Suppose that we had a random variable that was a constant. For example, we had constant service times. So there we said that statement 200, we said x is equal to 2.4. So it's obvious that every time I execute this instruction, I'm going to take the same value, 2.4. Okay, now why would that come out of the inverse transform method? So let me illustrate that. Suppose I looked at the service times and I drew their distribution function. So here is a distribution function. There's t. Here is the value 2.4. Now the distribution function of a random variable that is constant is a step function. That would be the value 1. because this function says that for every t that's less than 2.4, the distribution function is 0. The probability of being less than or equal to that is 0. And for every t that's 2.4 or greater, the probability of being less than or equal to that is 1. That's the same thing as saying that every value every random variable value takes the value 2.4. So this step function represents a distribution function for the random variable that has a constant value 2.4. So now if I apply the inverse transform method, that says what you do is you take your random number, you put it on the vertical axis, you project over to the curve and down. Well, the random number always falls between 0 and 1. With this step function, it's always going to project over to the same step, so it's always going to project down to the value 2.4. So therefore, although that inverse transform method isn't necessary to understand that this will generate the values for a random variable that always takes the value 2.4, this shows you that it also falls right out of the same formalism. So if you're trying to generate discrete random variables, it's the same idea, except that you project over to these various steps rather than over to a continuous curve. Okay, so now let's go and look at homework number 2. It says reliable intuition with a question mark. And the reason that the question mark is there is because the waiting time paradox, it seems to be true that most people don't understand why it should be that the average time between taxis is 1, but the average time that I have to wait for a taxi is 1, and the average time by which I missed the last taxi is 1. So therefore, the average time between the taxis that I arrived in between is 2, and 2 is twice as big as 1. That doesn't seem to make any sense. That's why it's a paradox, so we want to investigate that. So it says, here's homework 2. Consider a renewal process. Let x be the interrenewal times, and let I and r be the length of an interval interrupted at random and its remainder respectively. And it says the following basic simulation calculates the average values of x, I, and r based on 100,000 replications, and then it asks you to, in part A, run the simulation, which I'll go through in a moment, for the case where x is exponentially distributed. So that, in fact, is the case of a Poisson process. And then it asks you to do it for another case. And in both cases, it asks you to comment on the assertion, which is stated here, which, as you'll see, I think the assertion is intuitively obvious, but the theory will say that it's false. And so the question is, well, what's going on here? All right, so here's the basic idea. We have this renewal process. So with the renewal process, we have these intervals, which I'm calling x. So what I'm going to do is I'm going to sample from this urn, and I'm going to sample until I get to some point t. So in our taxi problem, that's when you arrive for a taxi. And so when I sample, I get a value of x and another value of x, and I keep on adding them like that. And I stop as soon as the sum of all of the x's exceeds t. So that's the first taxi that occurs after time t. So that means that this value right here, which I call r, that's the length of time that you waited for a taxi. And this time, which I call a, that's the length of time by which you missed the last taxi. And this time t is the last x that you drew out of the urn. This value here is x1, x2, and so forth. And what the simulation does is it does this over and over again, and then it calculates the average r's and the average x's and the average I. This is I right here. And compares them to see what the answer really is. Okay, so here's statement 100. It says for J, equals 1 to, let's see, it's going to do 100,000. Now, you don't have to do 100,000. In fact, the more you do, the more accurate this would be. I guess you don't want a comma in there. the more samples you take from the urn, the more accurate your answers are going to be. But of course, the longer it's going to take the simulation to run. But nowadays, I think you can do 100,000 in a wink of an eye. So you could do 1,000,000, for example. No big deal. Statement number 110. S, which is going to turn out to be defined as the sum of the inter-arrival times, the x's, you initialize that to 0. Statement number 120. The way it's written, it says t is equal to 100 minus 500 times the log of 1 minus RND. So every time I'm going to do this, remember I'm going to do 100,000 times, I'm going to generate 100,000 different R's and 100,000 different T's, and so 100,000 different R's and 100,000 different I's. So every time I do it, I'm going to want to pick a different T. I don't want to use the same T all the time. So I'm going to pick my T at random. And I want to pick my T to be far enough away from the origin so that there is no finite effect. So I want to imagine that this 0 is so far in the past that there's no memory. And the reason that I want to make it very far away is because I don't want things to get synchronized. For example, suppose that the x's happen to be all constant. If they're all constant and the t is the same value, then of course you're going to get the same thing every time you do it. So I'm going to make the t random, and what I'm going to do is I'm going to make it 100 units away from the origin plus 500 more. And this is going to make it random. Now that may be too far away. So you can play with this. You can choose these numbers to be different. The point is that you want to make the t so that it's random with respect to the initial conditions. And you can, of course, simplify this by replacing the 1 minus RND by the RND, which would probably be a good thing in this case because you're going to do this so many times that you want to save every cycle you can. Okay, so this thing is just to make the t far enough away from the origin so that the initial conditions have no effect. Okay, statement number 130. So now I'm going to reach into the urn and I'm going to pick an x. Of course, in the case it's a Poisson process, the x's are going to be exponential. Then I'm going to count. I want to count how many x's I pick, so I'll have c is equal to c plus 1. This will count the x's. Then I want to accumulate the x's. So statement number 150 tells me that the sum of the x's is whatever it was before plus the x that I just generated. Now, I'm going to do this for the purpose of calculating the average value of x at the end of the whole experiment. Because the average value of x, that's going to be the value that I'm going to compare with the r and the I, because that's the paradox, that things don't seem to work out the way you would expect. And statement 160, I'm going to say s is equal to s plus x. This represents the sum of the x's for the individual experiment. So I'm going to set this one back to 0. Okay, here's number 170. This is the key. If the sum of the x's is less than t, then I want to go to 130. So when I go to 130, I pick a new x, I count it, I accumulate them, and then I compare that to the t, and I keep on doing that. And let me tie my shoe before I fall down. Okay. Okay, so this loop, I'm going to go through this loop over and over again until for the first time the sum of the x's is bigger than t, which means that for the first time a taxi has arrived after my arrival point. And then at that time, I know how long I waited for the taxi. I know how long the time between taxis was. So now I'll say statement number 180. I'll say the remainder r is equal to s minus t, and I is equal to x. In BASIC, at least in QBasic, my BASIC, I can write two instructions on the same line. So this colon separates them. If you don't like that, you could call this 180 and that 185, say. 200, 190. The sum of the r's is equal to the sum of the r's plus r. In other words, I'm accumulating the sum of the remainders. And similarly, the sum of the i's is cumulated, the sum of the i's plus I. 200, next j. So I'm going to go through this loop j times, which in this representation is 100,000 times. But you could do it more. In fact, I'd like you to do it more. And then statement number 210, I'm going to print my answers. So I'm going to print. Let's see, Sx over c. So Sx is the sum of all of the x's divided by c. That's the number I counted. That's going to be the average value of the times between arrivals. Okay. In our taxi example, that value is going to be 1. Then it wants you to print Si over 100,000. So there's going to be 100,000 values of the x, which is called I now, 100,000 values of the intervals that cover your arrival point. I'm going to divide that by 100,000. So this is going to give me the average value of the x that was drawn out of the urn on the last trial. And then I'm going to ask it to calculate, similarly, the sum of the r's over 100,000, which is the average length of time that I had to wait for a taxi. So part A, this is exactly the same problem that we discussed earlier. Part B, it's the same, except I'm going to change the distribution of x's from something that's exponential to something that isn't. Don't forget that if you decide to run this thing for, say, 1 million instead of 100,000, to change the values down here as well. Okay, so what happens? It says, run the simulation for the case when x is exponentially distributed. That is, the renewal process is a Poisson process with the expected value of x equals 1, and fill in the following table. So that means that the statement 130, now you're going to generate a Poisson process. So x would be equal to minus 1 times the log of 1 minus a random number, and we can make it run faster by replacing 1 minus RND by RND. So this instruction will generate taxis with an average of 1 hour apart, if we call the units hours. Okay? Everything else is right there. Then it says fill in the following table. So here's your table. The average x, and it asks for theory and simulation. And the average I, and it asks for theory and simulation. And then the average R, and it asks for theory and simulation. Now, if the Markov property argument is correct, then the average x will be 1. Well, it's 1 regardless of that, because that's how you generated them. So the average x should be 1 in theory, and in simulation should be pretty close to that. If it isn't, then something is wrong. The average I, now, according to our theory, this is the waiting time paradox, will be 2. And the simulation will tell you whether it's 2 or not. And there won't be any doubt between 2 and 1. In fact, when you run it, you'll see that it's almost exactly 2. It has to be, because that's what the theory predicts. Theory can't be wrong. And the average R, of course, will be 1. So that's the theory, and the simulation, of course, will support that. And then it says, comment on the assertion. It is intuitively obvious that the average I, the average interval during which you arrived, is the same as the average x, because in fact it's one of the x's. It's the last one that you got in that process. And the average r, the average length of time you wait for the taxi, is equal to the average x over 2. Of course, that's your so-called intuition. Most people's intuition. That's why this is a paradox. So it says it's intuitively obvious that this is true. But when you run the simulation, of course, it won't be true. Because, in fact, the theory predicts that the average I is twice the average x, and the average r is not half the average x, but is the same as the average x. So when you run the simulation, that'll answer the question, which is correct. And, of course, it'll be that the theory is correct, and so it asks you to comment on the assertion. And when it says comment on the assertion, that means, well, say whatever you want to say to try and explain it. I mean, one comment could be the assertion is false, and then go on to do something else. But that's not really very helpful. So what I want you to do is I want you to think about this and try and come up with some kind of explanation as to why it is that the theory differs from what most people's intuition would be. And the simulation will show that the theory is in fact correct. Any comments at that at the moment or questions? Yes?
So on X, that came from
The x came from the fact that in our simulation we're generating x's from this urn. That's how we're going to construct this process. And in statement 130, we're making the x's exponentially distributed. That's where the log comes from, with an average of 1, because I'm multiplying by 1. So the x's are exponential with an average of 1, which means that we have a Poisson process of taxis arriving at a rate of 1 per unit time, whatever that may be. Yes? Adding a constant. Oh, okay. The question is, you mean here? Or what do you mean? I'm not sure what you mean. I didn't get to part B yet. Okay, so we're still on part A. All right, so part A will answer the question that was raised at the end of the last lecture, which is right, the intuition of the theory. Of course, the theory has to be right. This is going to prove that the theory is right, and is going to ask you to come up with an explanation as to why that is. Okay, now part B. It says, let x equal y plus u, where u is a constant, which will be treated as a parameter, and y is a random variable with a certain probability distribution. All right, so let me erase this. Okay, so now it's going to say, we're going to take part B, and that means that x is now y plus u. So what I'm going to do is I'm going to generate values from an urn with a distribution y, and then I'm going to add to each value I pick a constant. So when u is equal to 0, x is the same as y. And when u is equal to 0.5, then x is equal to y 0.5 and plus 0.5 and so on. So I want to have a sequence of different x's which differ from each other on average by simply the value of u. Okay, now it says let x equal y plus u, where u is a constant and y is a random variable. All right, so we have that the probability that y is equal to 1 is equal to 0.9, and the probability that y is equal to 11 is equal to 0.1. So now we have to replace instruction 130. So instead of generating values that are exponentially distributed, now the random variable is going to be discrete. 90% of the values are going to have the value 1, and 10% of the values are going to have the value 11. And then to each of those values, I'm going to add this value, this constant u, and so I'm going to get an x whose expected value is the expected value of y plus this constant u. It says, run the simulation and fill in the values indicated in the table. Calculate the theoretical values of E of I and E of R according to these formulas, which will be derived later. Okay, so now I'm going to say that the expected value, of course, what you have to do is you have to derive the instruction that's going to be here for 130. Okay, then you have to calculate the expected value of I in theory. And the expected value of I is equal to the expected value of x plus the variance of x divided by the mean of x. Okay, now this is theory that'll come later on in the course. And in fact, this works for the exponential as well. In the exponential case, it turns out that the variance is always equal to the square of the mean. So therefore, this formula would say that this term is the average squared divided by the average, or in other words, it's the average. The average plus the average is twice the average, which would say that the average covering interval is twice the average value of the length of the interval, which is exactly what the Markov property tells us. But there we argued by means of the memoryless property. And here, there is no more memoryless property. There's a general formula, and it holds for the exponential and holds, in fact, for every case. So we'll prove this later on in the course. But for right now, this is just a calculation. So all you got to know is how you calculate a variance, how you calculate the mean, and then you do this arithmetic. Then it also says that, and this is obvious, that the average value of the remainder is equal to 1/2 the average value of the interval. So in other words, you're going to calculate the average remainder, and you're going to do it by taking this formula right here and then dividing it by 2. Okay, so this will all work for Part A, except that you didn't need it for Part A because Part A was special. Then it says, draw the theoretical graph of E of R versus U. Okay, and you're going to fill in the table. So the table is going to look like this. First, you have the values of u. So u is the parameter that you're adding to the x. So first, you're going to run the simulation with the u's equal to 0. And then you're going to run the simulation with the u's equal to 0.5, and then 1.0, and then 1.5, and so forth, down to 5.0. So this may take a little bit of patience on the simulation, but not much. These things run very quickly. So what you're doing is you are letting the x, the length of the times between taxis, get bigger and bigger by always adding in a constant value. And of course, the expected value of x is the expected value of y plus u, which is the expected value of y plus the expected value of u. And the expected value of u is u, because u is a constant. Okay, so you're going to run it for each of those different values of u. And then you're going to calculate the expected value of x. And you're going to do that using theory and simulation. Okay, of course, theory comes right from here and the definition of y. So this is easy. Then you're going to calculate the expected value of I. Again, theory and simulation. Okay, the theory value of I is right there. In the simulation is just when you get what you get when you run this simulation with this instruction, and u replaced in the first case by 0, then in the second case by 0.5, the third case by 1.0, and so forth. So you're going to run the same simulation multiple times. And then you're going to calculate the expected value of r. So remember, I is the time between taxis, between the taxi you missed and the taxi you get, and r is the time that you waited for the taxi. Again, theory and simulation. Theory is here. Okay, so you do that and you fill that in, and then it says draw the theoretical graph of E of R versus U. Okay, so let's go over here and draw this graph. So here is the average time that you wait for a taxi, and here is u. Remember now that the length of time you wait for the taxi, the length of time between taxis, I should say, is equal to y plus u. So therefore, the expected value of x is the expected value of y plus u is the expected value of y plus the expected value of u, which is the expected value of y plus u. So you calculate the expected value of x from here, knowing what the distribution of y is, and so you get the expected value of y, and then you run the simulation in which the times between taxis are given by y plus, in the first case, u would be equal to 0. In the second case, it would be 0.5. In the third case, it would be 1.0, and so forth. So what happens is, as u is getting bigger, the average time between taxis is getting bigger. For a question? Okay, so as u is getting bigger, because remember, x is equal to y plus u. And here's your urn with the x's. So the way you're going to get the x's is you're going to sample and you're going to pull out the y's, and then every time you get a y, whatever it is, you're going to add u to it. And then you're going to take those y values and you're going to generate the taxis. So that's going to be y1, and this is going to be y2, and so forth. So when u is equal to 0, then the average time between taxis is the same as the average x. When u is equal to 0.5, the average time between taxis is the average y plus 0.5. So as u gets bigger, the average time between taxis gets bigger. So what you want to do is you want to calculate these values for different values of u. So here's u equals 0, and 0.5, and 1.0, and 1.5, and so forth. And so it says that, comment on this assertion. Quote, "It is intuitively obvious that as the average length of the random interval x increases, that is, as u increases, because we're adding that u to each x, to each y, the average length of the interrupted interval and its remainder r will also increase." So obviously, common sense, if I'm going to make the times between taxis get bigger, this is on average, this is exactly half an interval, half a second, whatever the units are, bigger than here. And now it's 1 second bigger than here. And now it's 1.5 seconds bigger than here. Because I'm always, in each run, as u gets bigger, I'm simply making the times between the taxis, which are the y's, get bigger and bigger. So as the time between taxis get bigger and bigger, if you arrive at random, the length of time you must wait for a taxi should also get bigger. How could it get smaller? How could it be anything else? That's my intuitive assertion. Now, when you make this calculation, you'll find that it predicts the reverse. That it predicts that as the time between taxis gets bigger, the time you have to wait for a taxi gets smaller. Sort of unbelievable. Okay, but what you're going to find is you start out with a certain value. This is your average waiting time. And then when you increase the time between taxis, the average waiting time is a little bit less. And then when you increase the time between taxis a little bit more, it's a little bit less. And then it starts to rise again, and then it does exactly what you would expect. That is, the time you have to wait for a taxi increases with the time between taxis. But at first, the theory predicts that it decreases. That's easy to see when you actually calculate these values and plug into these formulas. Is there a question?
You should have calculated the
Well, that's part of the question. But actually, there's a simple answer to that, which is that the variance of a sum, I should repeat your question, right? Okay. The question he's asking is when you increase the y by u, how do you calculate the variance of the x, which is now the variance of the sum? There's two ways. One is to calculate the distribution of y plus u directly, and then calculate the variance from that. But that's unnecessary because there's a theorem that you learn in stochastic models which says that the variance of a sum is the sum of the variances if the random variables are independent. And the u being a constant, of course, is independent of the y. So therefore, the variance of the sum is the variance of y plus the variance of u. But what's the variance of u? It's 0 because u is a constant. So the expected value of x is the expected value of y plus u. The variance of x is the variance of y. This u does not change the variance. It only changes the expected value. Okay, so you make those calculations, and then you put them in this table, and then you draw the graph, and the graph predicts that at first, as the time between taxis gets bigger, the time you have to wait for a taxi gets smaller. And that seems to be as counterintuitive as anything I can think of. And so it says, comment on this assertion. It's intuitively obvious that as the average length of the random interval increases, the average length of the interrupted interval and its remainder will also increase. But the theory predicts the opposite. The simulation will tell you what's going on. That is, it'll tell you which is true. And then you have to comment on it, which means you could say, well, you could say anything you want. Okay, but hopefully you're going to give an explanation as to whether or not the theory is correct, which of course it is, and then if so, why it's correct. So there's two arguments there. One is, of course it's correct, and your statement about intuition, well, that's your intuition, not my intuition. I know that it would go in the opposite direction. I can't argue with that because how can I say what your intuition is? But if you have the same intuition as anybody else, your view would be that as the time between taxis increases, the time you would have to wait for a taxi if you arrive at random would also increase. And so if the simulation and the theory shows you that it doesn't, then it would be nice. What I'm asking you is, can you give me an explanation as to why? In other words, once you know the answer, can you justify it? Okay, any questions about that? All right, so I'll get back to this next time if there are any questions. I think when you try and run it and read it more carefully, you'll see what the point is, so you can ask meaningful questions. And my impression of it is that this is a insightful, surprising result, and it'll give you some better understanding of why queuing theory and stochastic processes is tricky business. So any questions before we quit? Okay, so I'll see you all next time. And remember, next